Hello everyone, this is video 4.4 and 4.5 covering the distributive property, which is section 4.4, and some mental math stuff for section 4.5. So let's get started. So your textbook calls this the most important and computationally powerful tool in all of arithmetic. And when I first read that, I thought, well, there's no way. That's a pretty big statement. And really, I guess the key is this part here, the arithmetic part. If I really limit it to just that, which is, what the book says, if it's not the distributive property, I don't know what would be. So when I first read this, I was a little reluctant to accept that as a true statement, but I don't know that I could refute it with something else. So there might be something to that. It is, for certain, a powerful tool, but the most feels like a stretch. But I may have to go along with it. Um, I do want to sort of remind you that as we introduce multiplication, we sort of need to also remind ourselves of our order of operations, which a lot of you will probably remember as PIMDOS, this little mnemonic. So we have our parentheses, which really includes all grouping symbols. So if you have square brackets, if you have like that, those count as grouping symbols, and they're not parentheses, but they qualify in this grouping symbol level. Then after that, we have our exponents, which will also include roots, because a root is also an exponent. Then we have our multiplication and division, and these we do from left to right. And then we have our addition and subtraction, which also go from left to right. So here's our PEMDAS. So the parentheses is a little bit of a generic term, and we have multiplication and division, which looks like they're in that order of multiplication and then division, but these are equivalent and these are equivalent as far as the order goes. So now that we're adding multiplication and division soon, we should probably take a moment to remember order of operations. So we have our distributive property here, and I want to look at this in terms of a rectangular model for the distributive property. So this is the property itself, written in sort of a formula way. There's a verbal or a written definition that's in the book that the product of a number with a sum is equal to the sum of those products of the first number with the terms in the sum. That's a little wordy, I know. So if you remember it in this sort of formulaic way, you won't go too far wrong. Keep in mind this could be a sum or a difference. So I feel like we see the distributive property mostly as a sum, but it also works over a difference as well. So I've also seen some teachers who like to draw these little arrows, and some places, I've been in schools where they call it a rainbow. They make it like a little rainbow. I've been in schools where they talk about bombing the fort, which seems a little harsh. But however you want to sort of remember and point out for students this process, whatever sort of memory tool, that's fine, as long as the understanding is there. So let's look at these two models. So we'll take our first rectangle, and so this is our A, and then we'll split this like this and say this is our B and this is our C. So the area of this full rectangle, well, this whole side is A, and this whole side is B plus C. So we can see the left-hand side here, the left-hand side, LHS, is this full rectangle, which is A times B plus C. Now this is also equal to the area of these individual rectangles. So this would be A times B, and this would be A times C. So this area can be taken as one full area, like the left-hand side, or can be taken as this partitioned area on the right-hand side. Let me fix that. There you go. So here's my AB plus AC. Now, the same thing can be done for the subtraction version, the difference version, but we have to set this up a little bit differently. So here's our full thing is the B and then minus the C. And what we're looking for is this area here, right? So this kind of goes back to what we talked before about models of subtraction, because my B minus C, I'm not going to do a length of B and then add on the C so I can take off the, no, subtraction is the removal of something. So this is no good. We don't want to do that. B minus C is going to be some length B, and we're going to remove this length C. And so this is what we're looking for in here. So the full area here could be, or yeah, the full area could be this A minus B, this full rectangle here, minus this area here, the AC. And so this would be my right-hand side. And so this would be my area in here. The left-hand side is going to be just A times this length. And this length right here is B minus C. That's how long this is. So this shape in here is A times B minus C, which is my left-hand side. Both of these work, both of these apply, both of these show the distributive property. Again, I feel like we see the addition version of this a lot more than the subtraction version, but both of them apply. And I want you to take a moment to sort of appreciate how much of the previous models that we've used, we've talked about the area model for multiplication, our set removal or set combination models for addition and subtraction. There's a lot that's going on here that we need to put in place before we get to these models. But we've covered all of this, but it should show the interdependence of all these models as we get to this point. So I want to take a second to look at these two examples, because I feel like a lot of times when we see the distributive property, we see this version. We see distributing to the right. And so A times B plus C, here's A times B, here's A times C. And so we get AB plus AC. But this also applies going to the left. So this can distribute here and here, and we still get AB plus AC. So this is an extension of this idea of commutativity. This product of A times this sum, B plus C, can be multiplied in either order. It can be A times the sum or the sum times A. It doesn't make a difference. And so the order in which I put them means that A is either going to distribute to the right or to the left. You might think, well, if it doesn't make a difference, why don't we just always put the A on the left? This doesn't necessarily that you can't. But it's good for students to see this operating in both directions so they don't think the distributive property only works in one direction and not the other. It's also good if students see this as not just a multiplication operation, but also as a factoring or division operation. So AB plus AC, we notice that there's a common A, and this A distributes out. And so this makes A times B plus C. So there's a lot of ways this property can be used. We want to make sure that we show it in as full a scope as we can so students see the usefulness and the portability of this property. So let's look at a problem where we use distributive property to solve a problem involving subtraction. So suppose we're doing 8 times 19, and this sort of overlaps with our mental math section that's coming up in section 4.5. So if we think about what 8 times 19 looks like, we could think of this as 8 times 20 minus 1. And so what we're looking for is this area in here, because this would be not my 19. This full is my 20, and this is my 1 in here. I'll erase that from here. So I've split this 20 into 19 and 1. Well, the 8 times 20, the full rectangle, is going to be 160. That's the full rectangle in here. And I know this amount in here is 8 times 1, or 8. So I could think of this as 160 minus 8, which is 152. So what I've done is, I've done 8 times 19 is the same as 8 times 20 minus 1. And then when I do this distribution here, this is 160 minus 8 is 152. Why the 20 and the 1? Well, because 8 times 20 is relatively simple. It just means 8 times 2 with a 0 on the end, so that's 160. And 8 times 1 is pretty simple. That's just 8. And so if I know that 19 is 20 minus 1, those products of 8 times 20 and 8 times 1 are going to be a lot easier to work with in my head than trying to do 8 times 19. Can certainly argue, I mean, 8 times 19 is just, 80 plus 72, which is also 152. So we could think of this as an addition distributive property. Also split this into 10 and 9 by 8. This is 80, this is 72, so it makes the same 152. Either way works, but this method of using the 20 minus 1 gives us a way to illustrate how the distributive property with subtraction can be useful, especially in a mental math problem like 8 times 19. So building up to the algorithm for multiplication, we should look at a problem like 11 times 14, where we're going to use the distributive property twice. So we could take 11 times 14 and split this into 11 times 10 plus 4. And now we have 11 times 10 plus 11 times 4. So we've distributed that 11 to the 10 and to the 4. But now we can also take that 11 and split it up into 10 plus 1. And now this 10 will distribute and this 4 will distribute. So you can see the way these problems normally work out, we're going to distribute in both directions. So this 11 distributed to the right and this 10 and this 4 distributed to the left. And so we get 10 times 10, 10 times 1, 4 times 10, 4 times 1. And what this is going to look like visually, I've drawn that a little bit too much like a square, I'm worried. So we're going to break this into 10 and 4. And so now here's my 11 times 10 and 11 times 4. And now this 10 will distribute over this 10 and this 1. And so we've got 100 here, we've got 40 here, we've got 10 here, and we've got 4 here. 140 and 14 makes 154. The same thing that we get if we work this out here. And we are right up against the edge of the algorithm. So we're going to come back to this model when we look at the standard algorithm for multiplication. But it's important to see that this really comes from the distributive property. The normal, well, I shouldn't say normal, but the standard algorithm for multiplication is a generalization and an application of this distributive property. And this could apply to much larger. We could do 3-digit, 4-digit, whatever numbers we want, and we'll look at that when we get into that section, section 4.6 on the standard algorithm for multiplication. But hopefully you see how this distributive property area model works and can be applied not just once but twice. So, section 4.5 is on mental math approaches, and some of the stuff that we've looked at in this chapter and in other chapters lend itself toward this mental math approach. I don't have a ton to add to what's in the book, really. So if you want to have a look through it, and it's hard to do mental math as like a test question or a quiz question, because if somebody asked me to do something in my head, my tendency might be to grab a piece of paper and kind of work it out on paper to make sure that my mental math is correct, and then you're not really answering the question. It kind of defeats the purpose. What I do want you to think about, though, is the way that the models that we're using can help students, or even help yourself, form ways of thinking about mental math. If you go back and look at the area model problems that we're looking at for 1 times 2 or even 2 times 2 digit multiplication problems, trying to do the algorithm in your head is a lot of pieces sort of moving around, a lot of numbers floating around. And so it's hard to kind of keep track of what's going on. But if you have an area model and you're thinking about, well, I've got a square and 3 rectangles, and that's 100, and that's 40, and that's 10, and that's 4, and then add all those areas up, the mathematics is not necessarily any easier or any more complex, but the fact that you have sort of a cognitive structure, you have something to think about, and it allows you to sort of anchor your thinking, um, can really help in developing mental math approaches that have a lot of fluency and proficiency to them. So the the work that we do that's not mental, or strictly mental, some of the pencil, paper, or board work that we do to help create these models help students develop this mental math approach and their proficiency with mental math. So um, it's not a bad idea when you're looking at some models to stop and talk about how this can be applied in a mental math approach. Okay, so here's your checkpoint problem. So use the rectangular array or distribution model to show 26 by 43. And in the next video, we will look at the standard algorithm for this, and we can, we'll be able to apply that to problems like this. But we want the algorithm to be rooted in some sort of model, some sort of concrete idea. And so looking at this from rectangular array distribution model will be key to that. So if you have any questions about anything from this section, please by all means let me know. All right, thanks.